Today we're going to talk about hypothesis tests for one-sample means. Our assumptions and conditions are pretty much the same as they were with confidence intervals. We have independence assumption, in other words, are we dealing with a simple random sample? Also, our 10% condition, when a sample is drawn without replacement, the sample should be no more than 10% of the population, or in other words, population size is greater than 10 times the sample size. Our normal population assumption, we can never be certain that the data from a population that follows a normal model, but we can check the nearly normal condition. And this comes from a unimodal and symmetric data, and we can either do it with a histogram or a normality plot, if we're given the data. So the nearly normal condition is that the smaller the sample size, the more closely the data should follow a normal model. However, if the sample size is between 15 and 40, the t works well as long as the data are unimodal and reasonably symmetric. For larger sample sizes, the t methods are safe to use even if the data are skewed. So the conditions for the one-sample t-test for the mean are the same as the one-sample t-interval. We test the hypothesis that the null, mu, the population mean, is equal to some number, using the statistic t sub n minus 1, which is the degree of freedom, is equal to sample mean x bar minus mu sub 0, which is the population mean, over the standard error of the sample. Now the standard error of the sample mean is s over the square root of n. When the conditions are met and the null hypothesis is true, this statistic follows a student's t-model with n-1 degrees of freedom. We use that model to obtain a p-value. To find the probability using a t-distribution, we have a sample size of 7. We're going to have t equals x minus x bar over s. Our x is going to be 2.01. Our mean is 2, standard deviation 0.109. So we find a t-score of 0.0917. Now in the calculator, we're going to go to second vars, number 6. We have negative infinity for our lower bound. For our upper bound, we have 0.0917. Our degree of freedom is the sample size minus 1, so 7 minus 1 is 6. And we're going to paste this into the home screen, and we get a probability of 53.5%. Now, you cannot do this on the calculator using the mean of 2 and a standard deviation of 0.109. You have to convert these to a t-score, as you can see from the screen here. So let's take an example. Is the mean weight of female college students still 132 pounds? To test this, we take a random sample of 20 students, finding a mean of 137 pounds with a standard deviation of 14.2. We're going to use a significance level of 0.1, which is basically saying this is our alpha. So our hypothesis is that mu is the population mean weight of female college students. Our null is that mu equals 132. Our alternative is that mu does not equal 132 because in the problem it doesn't say one way or the other, it just wants to know if it's still 132. Our assumptions and conditions. A simple random sample is stated. Since sigma is unknown, we're going to use the t-distribution. We're going to assume approximately normal distribution because we do not have the data. And our population size is greater than 10 times 20. I think we can safely assume that. So, calculating the test statistic, we have 137 minus 132 over 14.2 over the square root of 20. This gives us a test statistic of 1.575. So, drawing our normal model, we have here two shaded parts because it's a two-tailed test. Since we have 1.575, that's going to be here on the right. And we find that p-value, which is 0.066. And we're going to double this because we're looking at a two-tailed test. So the probability that a sample mean would equal 137 given the population mean equals 132 pounds is equal to 0.132. So our conclusion is, since p-value is greater than alpha, and our alpha was 0.1, we failed to reject the population mean weight of female students is 132. All right, another example. A father is concerned that his teenage son is watching too much television each day, since his son watches an average of 2 hours per day. His son says that his TV habits are no different than those of his friends. Since his father has taken a stats class, he knows that he can actually test to see whether or not his son is watching more TV than his peers. The father collects a random sample of television watching times from boys at his son's high school and gets the following data. Is the father right? That is there evidence that other boys average less than 2 hours of television per day? So our hypothesis is mu equals the population mean number of hours watching TV. The null is mu equals 2 hours, and our alternative is mu is less than 2. Because in the problem it says, is there evidence that other boys average less than 2 hours? So they're talking about the alternative. Our assumptions and conditions. We have a simple random sample, and it's stated. Sigma is unknown, so we're going to use a t-distribution. And our population size is greater than 10 times our sample size. Next, we do a normality plot based on the data, and since the normality plot looks linear, we have an approximately normal distribution. So calculating the test statistic, we have 2.01, which happens to be the mean of the data, minus 2, our population mean, over 0.345, which is our standard deviation of our sample, over the square root of 10, and we get 0.0918. Since this is a left-tailed test because our alternative said less than 2, we're going to shade to the left of our test statistic. We get 0.5356. So the probability that we get a sample mean equaling 2.01, given that the population mean is 2, is 0.5356. So we can conclude, based on an alpha of 0.05, since it's not given, the p-value is greater than alpha, we fail to reject the population mean number of hours watching TV by other boys is 2. In our head, we're saying we accept the fact that the mean number of hours watching TV by his peers is still 2 hours.